Hello guys, welcome to our second video in the stereochemistry series. Let me tell you that today's video is very important because today I'm going to tell you how to draw a three-dimensional molecule on a two-dimensional paper or screen. So we will be discussing different projection formula today, which will help you, of course, in drawing a three-dimensional molecule on a two-dimensional paper or screen. So I would suggest that you watch till the end, stay focused, and do not skip. Learning how to draw a three-dimensional molecule on a two-dimensional paper is very important, because if you cannot do it correctly, you would not be able to determine the correct stereochemistry of a molecule. And one more thing, for learning stereochemistry, you must have a very strong imagination power. This is important because you'll be dealing with molecules in the three-dimensional space, and you won't have the molecular models every time to determine the stereochemistry of a molecule. So the only way to do it is to imagine the molecule in space and imagine how the various groups are oriented in space relative to each other. So let's get on with it. So we'll be discussing different projection formula for organic molecules, which are of course having three-dimensional structures. And these projection formula will help you in drawing these molecules on a piece of paper. But first, let's see how these groups are drawn or shown in 3D. So you have to first show the molecule as if it is a 3D structure. But because you're dealing with a two-dimensional screen or a two-dimensional paper, you cannot show a three-dimensional structure on a 2D paper. So to actually show it, you need to have certain notations or drawings or projections, and that is how we do it in organic chemistry. So you will find these projections or drawings in different books, and if you don't know what they mean, I'll tell you today. So we draw these molecules or the groups attached to a particular atom in the molecule with bonds, of course. So these covalent bonds are shown with such type of lines. But to show a three-dimensional molecule on a 2D paper, or to show the correct orientation of groups relative to each other, we draw them with different bonds or different lines. So if you see a group drawn with such a line, a solid line, it means that that particular group or atom is in plane. Now what does this in plane means? In plane means that you are drawing the molecule on this screen or this paper. This screen or paper is two-dimensional in nature. So there is a plane, a two-dimensional plane of this screen. So if you are drawing a particular atom or group with this solid line, it means it is in plane of this screen. Right? It is not coming out of the screen, it is in the screen. And so we say that this group or this atom or group of atoms is in plane. You must have also seen such type of a bond. Now we call it a solid wedge. So it looks like a wedge and it is filled inside. It's a solid wedge. Now if you see any atom or group of atom drawn with such a solid wedge, it means that that particular group or atom is above the plane. Now above the plane means it is towards the viewer. Now right now you are sitting in front of your screen. Your screen is two-dimensional. your central atom to which this group is attached is in this screen, and the atom or the group that is attached to that particular central atom is coming out of this screen, and it is towards you. Now you are sitting in front of the screen, so it means that this group is also projected outwards towards you. It is in front of the screen. This group or this atom drawn with this solid line means it is in plane of this screen, and if you see a solid wedge, it means the group that is right here is coming out of the screen towards you, and we say that it is above the plane of this screen, or above the plane also means that it is towards the viewer, it is closer to the viewer. If you see any atom or group of atom drawn with this dotted line, broken line, it means that this group which is here attached to this central atom is also out of the plane of this two-dimensional screen. But in this case, this group which is here is going behind this screen. And so if this is the plane of the screen, it is going behind the plane of the screen. In other words, you are sitting in front of the screen, but this atom or group of atom, it is going behind the screen, so it is moving or projected away from you. So we say that it is away from the viewer. So anything that is away from the viewer is also said to be behind the plane or below the plane. So first you have to understand what these different types of bonds mean in stereochemistry. So solid line means the group is in plane. A bold wedge means it is towards the viewer, it is closer to the viewer or above the plane. And a broken line means that it is behind the plane or it is away from the viewer, in other words. So the very first and important projection formula is the Fischer projection. So how do we represent or draw a molecule using Fischer projection? Now this Fischer projection looks like this. So we have a central atom, a central carbon atom, and this central carbon atom has 4 groups attached to it. So A, B, C, and D are attached to this central carbon atom. Now if you see all these 4 different groups, A, B, C, and D, are drawn with solid lines. So you would think that all of them are in plane. No, this is not the case here. They are not in plane. In fact, they are oriented in a three-dimensional space. So what does it mean actually? This structure or this drawing means this. Now you see 2 of the groups A and B are drawn with a solid wedge, and the other 2 C and D are drawn with a broken line. And from the previous slide, you know that anything drawn with a solid wedge means it is above the plane or it is towards the viewer. So if you consider this central carbon atom to be right in this screen, then group A and B are above the plane or in front of the screen. It means if you are sitting in front of the screen, group A and B are projected towards you, and group C and D are drawn with a dotted line or broken line. So this means that these 2 groups C and D are projected behind the plane or they are projected away from you. Now you don't have to draw the Fischer projection in this form. You should always draw the Fischer projection in this form. So why I have shown you this drawing? This is just to tell you that anything drawn on the horizontal axis in a Fischer projection, in this case group A and B are drawn on the horizontal axis, are always, or it always means that they are above the plane or they are closer to the viewer, they are towards you. So even if you draw it like this with a solid line in a Fischer projection only, it means that A and B are above the plane because they are drawn on the horizontal axis. And anything on the vertical axis means that they are behind the plane. They are away from you. So group C and D drawn here with these solid lines do not mean that they are in plane, but in a Fischer projection, this vertical line means that group C and D are away from you or they are behind the plane. And now you can imagine, as I told you earlier, that you should have a strong imagination power. So now you can imagine that this central carbon atom has a tetrahedral geometry because it's an sp3 hybridized carbon having 4 groups attached to it. So it should have a tetrahedral geometry. So if 2 of the groups are projected outwards towards you and 2 other are projected away from you in this way, then it more or less forms a tetrahedral geometry, right? So what are the rules? The rules for the Fischer projection say that anything on the vertical bonds mean they are below or behind the plane, and anything on the horizontal bonds or on the horizontal axis means that they are above the plane or in front of the plane. So how do you draw it? You have the main carbon chain that is usually drawn in a vertical arrangement. So you draw the main chain, the main carbon chain on the vertical axis, and then the other groups are drawn on either side of the chain. But this can vary. It's not always important that you draw the main carbon chain on the vertical axis. You can draw it on the horizontal axis as well. This is not hard and fast. You can draw it anyway, but this is more convenient. If you draw the main chain on the vertical axis, this is more convenient and easier to understand, and then you draw the other groups on the sides of this chain on the horizontal axis. So that would mean that the other groups are above the plane and the main chain has carbon atoms that are behind the plane in this case. So this is not hard and fast. You can draw the main chain on the vertical axis or on the horizontal axis. That doesn't really matter. But these two rules are hard and fast. So vertical bonds in a Fischer projection would always mean that the groups are behind the plane, whether that is the carbon atoms of the main chain or they are other groups. But if they are on the vertical axis, it means they are projected away from you, and anything on the horizontal axis means that they are in front of the plane, and this is hard and fast. Now let's explain this with the help of an example. So we have this molecule, this is 2-butanol. So we have 1, 2, 3 and 4 carbon atoms in the chain, and on the second carbon we have a hydroxyl group attached. So this is 2-butanol, and this carbon right here is an asymmetric carbon. Asymmetric carbon that we will also discuss later is any carbon atom that has different groups attached to it. So it has 4 different groups attached to it. This carbon has a CH3 group, an ethyl group, C2H5 group, a hydroxyl group, and what is the 4th group? That is a hydrogen, which is not shown here. It is right behind this hydroxyl group, right? And from this 3D structure, you know, as I've already told you, that anything drawn with these solid lines mean that the groups are in plane of this screen. So this CH3 and C2H5, which are drawn with the solid lines, means that they are in plane. This carbon atom is in the screen. This CH3 and C2H5 are also in the screen. Now this hydroxyl group is drawn with a solid wedge. It means it is not in plane of this screen, but it is projected outwards, and it is projected outwards in front of the screen. And when you are sitting in front of the screen, it means this hydroxyl group is projected outwards towards you. It is towards the viewer. It is closer to the viewer. So we say that it is above the plane. Now, where is the hydrogen? Hydrogen is right behind this hydroxyl group. You cannot see it here, but it is projected outwards away from you, or it is projected behind this screen. So just for your understanding, I draw it like this. And this doesn't mean that the bonds have tilted or these groups have tilted. They are still in this form, but just to show you that there is a hydrogen group which is behind the plane and it is drawn with a dotted line. I have just tilted the bonds. Now this is a three-dimensional structure for a 2-butanol. How to draw a Fischer projection for this structure? To draw a Fischer projection for this molecule, you have to view the molecule from different angles. You can view it from different angles and then you draw a Fischer projection. Remember these rules, don't forget them, right? So if this is your eye, it means you are standing right here and you are looking at the molecule from this angle, right? So you can view the molecule from this angle, and then you can draw a Fischer projection. You can also view the molecule from this angle. So you're standing right here and this is the angle of your eye looking right at this central carbon atom and the other groups. You can also stand right beneath this molecule and look at it from this side, from under the molecule, and then you draw a Fischer projection with correct relative orientation of the groups. Or you can stand above this molecule and look at it downwards and then draw a Fischer projection. We will discuss each of these angles one by one in the coming slides. So let's see if we have this three-dimensional structure for 2-butanol and we are standing right here to the left of this molecule and looking at it from this angle. I have drawn this line just to show that this is a plane, and you see that your eye is above this line, right? And if you draw a line right through this carbon atom here, you see that two of the groups are also above this line. Your eye is also above this line, so it means that this OH group and this hydrogen group, they are closer to you, and anything that is closer to the viewer or towards the viewer means it is above the plane. So if we consider this line as a plane, these two groups are above the plane because your eye is above the plane. So these two groups are also above the plane because they are closer to the eye. And these two groups are projected away from you, away from your eye. And because you are above this line or this plane, these two groups are below this plane, or these are away from you. So we say that they are behind the plane or below the plane. Now, please stay focused here and try to understand. You are standing here to the left of the molecule looking at this carbon atom. Now, it means you are standing right in this screen, and you already know that this carbon atom is in the screen, in the plane of the screen. These two groups which are drawn with these solid lines are also in the screen, right? So CH3 and C2H5 are in the screen. OH and H are not in the screen. They are out of the screen. OH is in front of the screen. H is behind this screen, right? But now you are standing here. So this means that CH3, C2H5 and you are in one plane. So you are standing in plane of this CH3, C2H5 and this carbon atom. And OH and H are not in your plane. OH, because it is in front of this screen, drawn with this solid wedge means that it would appear towards your right, because you're standing here and your right is actually the front of the screen. So this OH is in front of the screen, so this will appear to your right, and this H is behind the screen, and when you're standing here, your left is towards the back of the screen. So this is at the back of the screen, so this will appear to your left. So when you draw a Fischer projection, it will look like this. So to the right will appear the hydroxyl group. To your left, you will see this H group because it is going behind the screen, and on the vertical line, you will see the CH3 and C2H5. Now, why I have drawn or written CH3 here up and C2H5 down? Because you're standing here, so, and you're looking at this angle, through this angle. So this CH3 is like above from your eye line. It is like towards your forehead, above your eye line. And this C2H5 is like towards your chin. It is below your eye line. So you just have to imagine it. So you draw the CH3 up and C2H5 down. Now we have drawn a Fischer projection with all solid lines. But from the rules, you know that anything drawn on the horizontal axis means they are above the plane, right? So this OH and H means they are in front of the screen. Now, in this projection formula, this OH and H are coming out of the screen. This carbon atom is in screen. H and OH are in front of the screen. CH3 and C2H5 are behind the screen. They are away from you. Correct? Now, let's check if we have drawn the correct Fischer projection. So what we actually need to check. You already know that anything on the horizontal axis means it is above the plane. So that is the rule, the hard and fast rule. So from the Fischer projection, now you know that H and OH, because they are drawn on the horizontal axis, are above the plane. So you have to check whether the horizontal groups, that is the H and OH of the Fischer projection, are above the plane in the 3D structure. So this is the 3D structure, and you have to check whether this H and OH were above the plane. Above the plane means with reference to you, with reference to the viewer. So you are standing here, your eye is above this line, this plane drawn here, and H and OH are also above this line. So they are closer to you, and anything close to the viewer or close to the eye means it is above the plane. So in the 3D structure, this H and OH were closer to the eye, means above the plane, and same is the case here. H and OH are drawn on the horizontal axis, and that means that they are above the plane. And then you check the vertical groups. So are the vertical groups in the Fischer projection, the CH3 and C2H5 of Fischer projection, behind or below the plane in the 3D structure? So you have to check whether the groups that you have drawn on the vertical axis in the Fischer projection, were they behind the plane or away from you in the 3D structure. So you are standing here, this is your eye above this plane, and this C2H5 and CH3 are on the other side of the plane, so they are away from you. And you can also see from the bonds that they are projected away from you. So they are projected away from you here, they are below the plane, and they are on the vertical line here. So it means they are also behind the plane in this Fischer projection. And so this is the correct Fischer projection if your answer is yes. Now we have the same 3D structure, and now I stand here and observe the molecule from this side, from this angle. So you are standing here to the right of the molecule now, and you are looking at this from this angle. again you are standing in plane of this screen. So this CH3 and C2H5 drawn with these solid lines are in your plane or in plane of the screen. OH is drawn with a solid wedge, means it is in front of the screen. So if you are standing here, the front of the screen is towards your left, and so OH will appear towards your left. And when you are standing here, this back of the screen is towards your right. So H is at the back of the screen, so H will appear towards your right. So you draw H to the right on the horizontal axis, OH to the left, and now because you're standing here, these two groups are in your plane, and this C2H5, because it looks like it is slightly further from you, or it is above your eye line, so it means it is towards your forehead, and this CH3 is like towards your chin. So C2H5 is drawn up, CH3 is drawn down. So in this case again, CH3 and C2H5 are on the vertical axis, means they are behind the plane, and they were away from you here as well. And OH and H are on the horizontal axis, means they are above the plane or closer to the viewer, and they were closer to the viewer even in the 3D structure. So you have to ask yourself those two questions again. So you have to check the horizontal groups in the Fischer projection and compare it with their orientation in the 3D structure. So in the 3D structure, H and OH are closer to the eye, means towards the viewer, and in the Fischer projection they are on the horizontal axis, means that they are above the plane again and closer to the viewer. So it is correct. The answer is yes. In both the cases it is the same. Here the CH3 and C2H5 are drawn on the vertical axis, means they are away from you, behind the plane, and same was the case in the 3D structure. They were away from you, away from your eye, projecting away from you in the 3D structure. So again, the answer is yes, and the Fischer projection that you have drawn is correct. Now let's observe it from a different angle. So you have the same molecule, and now you're standing underneath the molecule and you're observing it again from the plane of the screen. You are standing right in the screen and looking at this molecule in this carbon atom here. Now if you just imagine you're standing here and this OH and H are projected out of the screen. OH is projected in front of the screen because it is drawn with a solid line, and H is projected behind the screen, correct? And again we have the same line drawn here. So your eye or you are under this line, and H and OH are above this line. So it means they are projecting away from you, and you can also see from the direction of the bonds that they are projecting or pointing away from you. And the CH3 and C2H5 here, they are drawn in such a way or projected in such a way that they look as if they are towards you, and also they are below this line just like your eye, so they are right in front of you, so they are closer to you. So if you're standing here, these two groups are closer to you. So you're standing here, it's like you're standing in the screen facing towards the back of the screen and looking up. You will see CH3 to the right and C2H5 to the left, right? So you draw it on the horizontal line, and H and OH will appear on the vertical line. Now because you're standing here facing just like you're facing now, you're facing the screen, but just imagine as if you're standing in the screen and facing in the same direction as you are now. You will see that OH is like above your eye line towards your forehead, so you draw it above here, and H is towards your chin, so you draw it down here. Again, as I told you earlier, you have to have a very strong imaginative power to understand this, and again, don't skip it. Take it slow and steady and try to understand it. So you have the Fischer projection drawn like this. And again, you ask yourself the two questions. So you check the horizontal groups, in this case CH3 and C2H5 in the Fischer projection. Check if they were above the plane. Above the plane means if they were closer to you. Yes, they are closer to the eye in the 3D structure, and closer means they are above the plane towards the viewer, and anything on the horizontal line means in the Fischer projection it means they are above the plane. So they are above the plane here, closer to the viewer here, towards the viewer here, and also they are towards the viewer here. So you have drawn them in the correct way. And the vertical lines mean they are away from the viewer in the Fischer projection, and these two groups were also away from you in the 3D structure. So again, the answers are yes, and your Fischer projection is correct. Now, let's try it from a different angle. So you stand right above this molecule and look at it downwards. Again, you have drawn this line. And now you see that these two groups are towards the eye. These two are away from the eyes. They are in the same direction from this line, from this plane, and they are on the opposite side of this line. So they are away from the viewer. Now if you're standing here in the same direction as you are facing now, and you are looking, your face is down, your molecule is down, and you're looking at it, you would see that H and OH will be on the horizontal line. You see they are vertical. I just have drawn them in tilted form just to show you both the groups, but in fact they are right here straighter, both these H and OH. So if you are standing in the same direction as you are facing now, and you are above this molecule and looking at it down, you face downwards, you would see that H and OH are appear as if they are vertical, and H will be towards your forehead, imagine it, and this OH will be like towards your chin, below your eye line, right? So I draw them on the vertical axis here. H is towards my forehead, OH is towards the chin, and then this CH3 and C2H5 will appear towards your right and left. So if you're standing in the same direction as you're facing now, CH3 will be on your right as it is now, and C2H5 will be on your left. So I draw them here. Now I've already written here the answer is no, and the Fischer projection is wrong. Why? Let's see. Again, ask yourself those two questions. So the horizontal groups in the Fischer projection, that is the CH3 and C2H5, were these groups towards the viewer or above the plane in the 3D structure? No. Your eye is here above this line, and these two groups are below this line. So it means they are away from you. So they are in a way behind the plane. But here you have drawn them on the horizontal line, and anything on the horizontal axis in the Fischer projection means it is above the plane, it is towards the viewer. So in your Fischer projection, the CH3 and C2H5 are towards the viewer, they are above the plane. But in your 3D structure, they are behind the plane or away from the viewer. So these two structures, they do not correspond with each other, right? In fact, you have drawn it correctly corresponding to the angle from which you're looking at, but rules suggest something else. So this Fischer projection is not in correspondence with the 3D structure. Here these two groups were away from the viewer, but here these two groups are towards the viewer because they are on the horizontal line. And similarly, the vertical groups are away from the viewer in the Fischer projection, they are on the vertical axis, but here this H and OH were closer to your eye. So what does it mean? It means you should not look at this molecule from this angle. you have other three angles from which you can draw the correct Fischer projection formula. So you should not try this, because this may lead you to a wrong Fischer projection, and drawing a wrong Fischer projection means that it may lead you, and it will definitely lead you to wrong results or wrong conclusions. So the stereochemistry that you're going to determine from this Fischer projection will be different, will be in fact wrong. Right? So this is all about Fischer projection. I hope you have understood how to draw a Fischer projection for molecule. You can try this method on different molecules. You can you can find different examples and try it to draw a Fischer projection for different molecules. Still, if you have any question, you can write in the comment section and I'll be happy to answer. So, what are the things to do while drawing a Fischer projection? First, you have to draw the correct 3D structure of the molecule. Correct 3D structure means you should draw all the groups relative to each other in the correct direction or orientation. And then you have to view the molecule, or you have to imagine the molecule from such an angle or such a side, the first three that we have discussed, so that the groups which appear on the horizontal axis in the 3D. So when you look at this molecule from a particular angle or side, this 3D molecule, so anything that appears on the horizontal axis to you, they are projected towards you, while the groups which appear on the vertical axis are projected away from you. So if you just look at the last Fischer projection, the groups that appeared on the vertical axis to us, that was the H and OH group, which appeared vertical to us while standing above this molecule and looking at it downwards. This H and OH looked as if they are on the vertical axis, and they were closer to us, they were closer to our eye line. So that means that is not the correct way. So because anything on the vertical axis should be projected away from you. And the CH3 and C2H5 in the last Fischer projection, they appeared to us on the horizontal axis, but they were on the other side of that line which I had drawn. So they were projected away from us, right? So you have to look at the molecule from an angle where anything that appears on the horizontal axis is projected towards you, right? So you just scroll back, you go back and check the last Fischer projection and then apply this second point. If you have done this, then you are in a position to draw the correct Fischer projection. Otherwise, you change your angle, right? So this is all about Fischer projection. Let's discuss another important projection formula, that is the Newman projection. Newman projection is a drawing which represents the spatial arrangement or the arrangement of bonds or groups in space on two adjacent atoms in a molecule. When we weave the molecule along the bond joining two atoms, it means that you have to take two carbon atoms into account, and then you look at that molecule through the bond joining those two carbon atoms, and then you draw the groups attached to both the carbon atoms according to their spatial arrangement. So this is how a Newman projection looks like, right? So we have a dot right in the center of a circle. Now what does it mean? The dot is one of the carbon atoms, because you are considering two adjacent atoms, adjacent carbon atoms in this projection. So this is one of the carbon, and this circle means another carbon that is attached to this carbon atom through a single bond, and you are looking at this molecule from along the bond that joins this dot and the circle, right? And then the front atom, which is the dot here, and the rear atom, the carbon atom at the back is drawn with a circle, has different groups attached. So this dot, or the carbon atom in the front, has three groups attached to it, A, B, and C. So these groups are shown with spokes which are drawn to the center of the circle, and the center of the circle has this dot, right? And the rear carbon atom, which is shown with a circle, has three groups, D, E, and F, which are shown as spokes drawn to the periphery of the circle. So you see F is drawn from the circle, E is drawn from the circle, and D is also drawn from the circle. It means that D, E, and F are attached to the circle. Circle means the carbon atom that is away from you. Dot means the carbon atom that is closer to you. So this carbon which is closer to you, or the dot, has A, B, and C. You see they are these A, B, and C are connected to the dot, and the circle has D, E, and F. Now, how to draw Newman projection? So we will do it with the help of an example. So you have this molecule which has these two carbon atoms here and here. This carbon atom has three groups attached to it, A, B, and C, and this carbon atom has three groups, D, E, and F attached to it. Remember, both the carbon atoms are sp3 hybridized, so the geometry around them is tetrahedral. And now you see that this carbon atom has two bonds drawn with this solid line, so it means this group B and this carbon are in plane of this screen. This group C is projected outwards in front of the screen, drawn with the solid wedge, and projected downwards from this carbon-carbon bond. And this A is drawn with a dotted line or a broken line. It means it is projected behind the plane and projected downwards again from this this carbon-carbon bond. This carbon atom has a group D attached to it, which is again drawn with a solid line, so it is in plane and projected downwards. And it has group E and F, which are not in plane of the screen. F is projected outwards in front of the screen because it is drawn with this solid wedge, and E, drawn with a broken line, is projected behind the plane. Now, how to draw a Newman projection for this structure? For that, you have to view the molecule from an angle from where you see this carbon atom that is closer to you, and you cannot see this carbon. So you are looking at it along this carbon-carbon bond. See, your eye is right in front of this carbon-carbon bond. So when you are looking at it from this angle, you will see this carbon atom, but you won't see this carbon atom because you are looking it along this carbon-carbon bond. So you're standing here and you're facing this carbon atom right here. So you see this carbon atom is closer to you and this carbon atom is away from you. The carbon atom that is closer to you is shown as a dot right here. So you draw a dot, you put a dot here, and then you draw the groups that are attached to this dot. And we have group A, B, and C attached to the dot. So you're standing here right in the plane of this screen. This bond is in the plane of the screen. This carbon atom is in the screen, and this group B is also drawn with a solid line. So it is also in the screen and it is projecting upwards. So when you're standing here, it will appear as if this B is pointing vertically up. So you draw B here, and then as you're standing here, this C is projected outwards in front of the screen. So when you're standing here, the front of the screen is towards your right. So this C will appear as if it is towards your right and it is projecting downwards. See, it is pointing downwards. So you draw C to the right of this dot and projecting it downwards. And then you have A, which is behind the screen and projecting downwards. So it will appear to your left, projecting downwards. So now you have the front carbon atom with all the three groups attached in this fashion. Then we analyze the rear carbon. So the rear carbon is drawn with a circle. So you draw a circle here. And then you draw the groups from the circle, or those which are attached to this rear carbon atom or to the circle. So it has a group D projecting downwards and drawn with this solid line. So solid line means it is in plane of the screen and it is going downwards. So you draw D here straight down. It is drawn, this spoke is drawn from the periphery of the circle, but it should always point to the center of the circle. So you don't draw it from the center, but it should be in a direction as if it is pointing to the center of the circle. Then you have F, which is drawn with a solid wedge projecting upwards. So it is in front of the screen, and when you're standing here, the front of the screen is towards your right. So you draw F to the right and projecting upwards like this. Again, it is pointing to the center of the circle, but it is drawn from the periphery of the circle, means it is attached to the circle or the rear carbon atom. And then you draw E, which will appear to your left and projecting upwards. So this is how you draw Newman projection for molecule. This is very important in conformational analysis, which we will be discussing in the upcoming videos. I hope you understand now how to draw a Newman projection. The next one is a Sawhorse projection, and it shows, or it indicates, the spatial arrangement of all the bonds on two adjacent atoms. Again, these two carbon atoms, and this carbon-carbon bond in this case is drawn as a diagonal. So it is represented by a diagonal line, and then you draw the groups attached to each of the carbon atoms so as to have a tetrahedral geometry. So these are the three important projection formula through which you can represent or draw a three-dimensional molecule on a two-dimensional screen or a piece of paper. And from that, you can determine the correct stereochemistry or stereochemical identity of a molecule. I hope this lecture has helped you in understanding. Still, if you have any problem, you can write it in the comment section. I'll be happy to answer. See you next time. Thank you for watching.